Okay, so hello everyone. Do you still remember how to find the inverse on 3 by 3 matrix from your high school? Remember? um, Let me copy the last. Let's say we are using the same matrix as this matrix A. Let me copy this. Actually, in the textbook, especially this course, we don't really calculate until it 3 by 3. We only calculate the determinant 3 by 3. But for inverse, um, I think I can make some additional content. So if this A is the matrix, and we already calculate this yesterday, I believe this should be, let me check. It should be negative 44. So A, or determinant A is negative 44. Now, to find the inverse, we need to find another matrix. Let's say the new matrix that we want to find is, let's say, N. And this N is actually composed of each of the element is actually the determinant. Okay. Or let me write as the element of each. Let's say this is N11 and 1 2 and 1 3 and 2 1. Okay. Let's say we are writing this 1 1. Okay. So 1 1, if you remember the when we find determinant, if we cover this column and this row, then we will have this determinant, right? So we are writing all the terms on N as the determinant of these 2, 4, 5, 6, and then if you have this 2 and 1, we have this middle row and then the first column, and we have 3, negative 1, 5, 6, and we calculate all together. So 3, negative 1, 5, 6, and then 3, negative 1, 2, 4. This is 0, 4, negative 2, 6. And then this is 2, negative 1, negative 2, 6. And then this is 2, 0, negative 1, 4. 2, 3, 0, 2. 0, 2, negative 2, 5. Okay, and then we calculate all of them. Okay, we calculate. Let me move here. So this will be 12 minus 20 minus 8. Just let me know if I make miscalculation, okay? Because I haven't calculated yet. 12 this 18 minus 5, so plus 5. 18 plus 5, right? 23. 12, 14, right? 14. And then this 0 minus 8 is 8. Okay. And then the next one is 12 minus 2, right? Is 10. And then 8. And then 4, right? 18, 18 plus 5, right? 23. And then what? 4, 4, right? Okay. And then the next thing, we need to multiply with the sign of the cofactor. Still remember cofactor last time? The positive, negative, positive. Okay. 2, 3. This one? This wrong, right? Oh, should be what? 2, 3. Oh, yeah. 2, 3, negative 2, 5. 2, 3, negative 2, 5. Can you check the other one? Okay. Okay, right? Yeah, that's why is this is similar to the other. 10 minus 6 is 16. Okay, and then based on the signs, when we deal with the cofactor, we put into this whole number. Okay. Um, okay. So we got this result. Okay. It's still not the matrix that we want. Okay. Uh, now this a little bit tricky. So I will mark this diagonal. Okay? I will mark this diagonal. And what you need to do is you need to switch the the number. I think it's called the transpose, if you remember, the transpose of the matrix. But yeah, anyway, anyway, we need to switch this. Okay, so switch. So this negative 8 and 4 becomes here, and this part all changed to the other part, and negative 8 become here. So, or let me move to the next page so we can write with more space. So this become, I will write the diagonal first, because it's still the same. And this become negative 8, and this become 4, and this become negative 23, this become 14, and this become negative 16, this become negative 8. Okay. And the A inverse is 1 over the determinant and multiplied by this n, the inverse. And then also another way to evaluate the determinant is let me move the the matrix A. Let me copy to the new page. Okay, another way to calculate the determinant is adding the another column, right? Adding this first and second. I think in high school, some no, some of the teachers they teach this. So you repeat the same column here, right? Anyone who's learned this? And then what will you do? So first you are calculating the, I'll say, the right side, right? And then minus the other one, right? Let me draw the, so multiply here, multiply this, and multiply this. And we add them together. So 2 times 2 times 6 plus 3 times, or let me just go, the multiply all, okay? And let's see the results. So 4, 6, 24, negative 24, and then negative 5, okay? And then the other part, I may change the color, this part. And then minus the green one. Negative 1, negative 4, plus 4, 8, 5, plus 40, and then plus 18. Oh, it's too bright. Yeah. But is my calculation correct? Which one? Which one? Minus 5. Oh, here. So it should be 0. Just erase that. And then this should be 0 also, right? Okay, right? It's 306. And then the answer is negative 44, the same. So determinant A is negative 44. Okay. Whichever method you are using, I think uh, resulting the same number. Okay. Okay. Any questions? Any questions? So to calculate the final result of the A inverse, if we are looking at the matrix A, then this should be 1, negative 44, and then multiply with this. Okay. So yeah, quite huge and a little bit messy number. I believe the number is not prepared to be inverse, so it looks bad. Okay, uh, the next section about the matrix is the Cramer's rule. Have you learned that, Cramer? Maybe you've heard, but wow, what is that? Okay, but basically, Cramer's rule is a method to help us find the solution of linear equations. And probably you're wondering, do you know uh, what is the purpose of the matrix? Why we need to learn the matrix? You know, I'm wondering, because it's kind of still abstract for real life applications, right? Most of the math, calculus, right? But actually, uh, the matrix, because it has a set of like distinct uh, property when we are making any equations that we can model into subset of numbers. We can imagine, for example, when you are opening your laptops, you have the graphics, right? How to compute the graphics to process the image and make it looks like that. Okay? Maybe you're opening the windows and how to make that. So the basic concept of that is learning the linear algebra, how the computational inside the processors works, and that's the basic of the matrix. You know the pixel, pixel, right? It has like certain uh, set of the more the pixel is, your quality will be more accurate, right? More smooth, right? If your pixel is really small, like you can see if you download some image and maybe it's just like um, 20 kilobytes or maybe 50 kilobytes, and when you are zooming in, you will see the like rectangle, okay, like a rectangle like this, and this is maybe a color, but you will notice the rectangle here, right? So how to compute the image from like how the pixel is processed is basically we are using the world of matrix. Okay. And when we are uh, anyone using software for design, Illustrator, or anything? Yeah. Okay. So imagine you are stretching the image or maybe make it bigger. Okay. How to process that? You need to translate something, right? Like, for example, if you can imagine this like a graph x, y, you need to know how much these pixels move, right? The length you need to know, and how can you enlarge the pixels, right? And all of that is processed by the matrix. Okay, you can process or you can find, like, for example, I yesterday I mentioned the identity matrix, right? 111. Okay, and then there's other metrics, like for rotations. We have some identity for rotations, for translations, and etc. etc. And that's basically we need to multiply by that, and then the image will move. You get it? You get it? Okay. So imagine this is uh, like um, like an actual x and y, and you can translate this. You can make it bigger, Okay, and you can do anything that process and then make it into a pixels. Okay, so that's the idea for matrix. Okay, so for now maybe it's like a simple calculations, numbers, and then maybe some formula, but actually it's really useful if you at least, okay, you don't really need to memorize all, but at least you understand the logic behind this matrix. And then there's the movie like the Matrix, you know. Okay, I'm too old. No, you don't know the Matrix? No, right? No, right? Okay, okay. And that's also the same idea. It's the world where the all the like the computerized human mind, right? Yeah, that's that's the movie. Okay, let me write on the right side, or maybe in the new page. I think in the new page is better. So I will start with the Cramer's rule. Let me write the uh, some set of equations. Ax plus by equal r, and then x, y equal s. This is c and d. Okay, now if you want to solve this, and I want to use the elimination method to eliminate the by and dy. Okay, so I need to multiply the first equations with d and the second equation with b, so that this will be b dy and this is also b dy, and then I can subtract them, become 0. Okay, so let's do that. So multiply by d and multiply by b. Okay, and then this become let me use the other blue. So a dx, okay, plus b dy equal rd. Okay, and then bcx plus b dy is equal bs. Okay, and then I need to subtract all this to eliminate the terms b dy. Okay, so I will cancel this. So I get the result a dx minus bcx is equal rd minus bs. Okay, and then we can solve this solution if you want to find the x, right? So we can factorize x, and x will be, or I will write this as x ad minus bc. This is rd minus bs. So x will be, okay, and this is assuming, okay, assuming, let me write to make clear, okay, assuming ad minus bc is not 0. Okay. And similarly, if you want to eliminate ax and cx, we multiply with c and multiply with a. Eliminate this, we get this, and the result is y. Yeah, careful, careful. Okay, and similarly, we get as minus cr and then over ad minus bc. Okay. Now it has some interesting pattern that we can also use that in uh, in new equations. Okay. So you have the AD minus BC. Remember AD minus BC from the determinant, right? So if we are writing the equations, like for example, so if the linear system AX plus BY equal, that's using red color, and CX plus DY is equal S. Okay. The X is and dy will be and provided that it's not zero. Okay. And we can simplify this determinant, the formula, just by using the determinant. We write the determinant as if D is A, B, C, and D, okay, and the dx is R, S, and BD, and dy is or let's say this is the matrix first, the matrix. This should be the same thing. And this is AC. Then X is, well, let me use the black color. X is BX. Okay. So the idea, okay, at the end is when you solve for X, instead of A, B, C, D, you change all with X, AC with the RS, okay, and count that as determinant and divide by determinant of the A, B, C, D, okay. And the Y, you are changing the BD with RNS, okay? And in that way, you can solve and compute the X and Y easily. Okay? And later, the same way, if you are having X, Y, and Z, three, okay? It's like a thinking in the 3 by 3 matrix. Okay? And the same thing, determinant 3 by 3, determinant 3 by 3, but changing the X and changing the Y, changing the Z. Okay? And also, if you are applying with maybe higher degree, like 4, 5, it's also applicable. Also applicable. Okay. Okay, that's the basic of Cramer's rule. I will write another notes for Cramer's rule, the more official definitions. So Cramer's. So if a system of, let's say, n linear equation in the n variables, x1, or let me write in a different color, x1, x2, xn is equivalent to the matrix equation. Let's say dx equal b. Okay, this is basically what we did. Okay, the a, b, c, d, and then the rs is from here. Okay. And if the determinant of d is not 0, then its solutions are, okay. Now we are using n variables, meaning it can be x, y, z, and until any variables you can put in. Okay. Then its solutions will be x1 will be d x1, okay, over d, and then x2 and then and then xn. Okay, and then d is the matrix obtained by replacing the column. Let me write in the different color. This should be dx, dx. Let's say dxi. Okay. So it depends on which column, meaning it's x, it's y, or it's z. Okay. it's the definition of Cramer's rule. So let me go back here. So the idea is just replacing basically this is determinant, okay? But what you need to distinguish between x, y, z, we need just to exchange the column, okay? The column on, for example, in this case, the first column is we want to going to change. The first column is AC, and we change to the RS, okay? And here is the second column, okay? The second column, RS. Okay. And then that will be the solution for this particular equation, okay? And if you have like more, then you can focus on finding the determinant. Like for example, if you find maybe x, y, and z, then this will be determinant 3 by 3, which we already discussed how to find the determinant. Okay. Okay. Or maybe I will illustrate how we are going to find the 3 by 3. So example. So what if we are having equations like the first equation is having 3 variables, okay, x, y, and z. Okay. The second and third is only 2, x, z, and x, y. How we solve this? By Cramer's rule. Okay. So if you're looking at the second equation, it doesn't have any y, right? So we can compute y as 0. And here x, y, there is no z. So we can compute as 0. Okay. First, we can find the determinant, like only the d, and then we can find the dx, dy, and dz. So first, maybe we are going to look at d as in general equations. So let me write this as so 2, -3, 4, and it's 1, 6, 0, 3, -2, 0. And find the determinant. You can use this way and then plus plus plus, or the way that I did before. You just write the 2, 1, 3, -3, 0, -2. Okay, now let's calculate. Two zero zero -3 6 -54. Let me write here 0 -54 -8. So D is negative 62. 0, and 0. So what? The negative 38, right? Okay. Can you calculate? Is it correct? Correctly? Correct. And then we can solve one by one the dx. Dx is, what is the 105? 105, and then the other will be the same. So this will be 105 negative 302. Zero, zero. So the x is negative 90 plus 12. It's negative 78, right? This will be 2, 1, 3, and then 105. 105. And then 4, 6, 0. 2, 1, 3, 105. Is 20, 18, and the other is 0, 60, and 0. So dy is 38 minus 60, right? 60. This is negative 22. One more, dz. Okay, it's nice. Dz becomes 2. Can you check the dz? Is it correct? 217? 2 minus negative 15. Is correct? 70? 70? Minus 2, which one? Oh, this one. Okay. So this minus 2 plus 15. So 13. Okay. And then we can solve this and write the x is dx over d and y is dy and z is dz over d. So x will be negative 78, negative 38. And we can divide by 2, right? 2. And y is negative 22. Okay, and that's the answer. So Cramer's rule is another way to find um, directly the solutions from the determinant. Okay, but remember, you need to check the determinant first. Okay, this whole determinant, the d, should not be 0. Okay, should not be 0. This one. Okay, I think the section for the matrix is finished here, but still in the linear equation, we have on the other sections, it's up. It's actually the partial fraction. So if you are attending my calculus class, you already know what partial fraction is. Some of you maybe haven't, but some of you already found the partial fractions. So partial fraction is one way to solve or to simplify the rational functions. Okay. So let me go through the partial fractions now. Okay. Now let us see these fractions. Okay. I believe this is really basic. If you want to plus this two, what will you do first? What will you do first? Multiply the denominator. Okay. Okay. So let me write this x minus 1 to x plus 1. Okay. And what else? We want to find the top equations, right? So the bottom denominator, divide by each, and then you put them up here. Okay. So this will be 2x plus 1, okay, plus x minus 1. Okay. And then this is 2x, 3x, and then the other one is 0, so only 3x. And the bottom equations, let's just calculate 2x squared minus 2 plus 1 is minus 1. So there. Okay. So I can write this completely with the fractions. So the whole thing that refers here is called the partial fractions. And the conditions, if if the Rx is Px over Qx, R is rational functions. And then degree P is less than Q. And then remember that every polynomial with real coefficient with real coefficients can be factored. Can be factored into linear and irreducible quadratic factors, which means the linear is ax plus b, and the irreducible quadratic factors is ax squared plus bx plus c. And thus, we can express Rx a ax plus b and ax plus b let's say it's j. Okay. Now, um, this is actually, if you're already doing this in my calculus class, uh, it's the same thing actually, but in calculus, it's the method to simplify our integrations. Okay? So I believe this will be really helpful for the integrals. Okay? Okay, let me give you every case that's possible. So the first one is distinct linear factors. So we write this as okay. Now we have the example 5x plus 7, and then the x cubed plus 2x squared minus x minus 2. And please decompose these fractions into partial fractions. Okay. Can you try? So the first case, okay, from this example, if you see from the top equations here, the bottom will be linear equations, but it's distinct. So every A1, B1 is not the same as A2, B2. It's different, but it's linear factors. Okay. So first you need to think, can you factorize the whole thing here? Can you factorize? You need to use a little bit of polynomial um, long divisions or syntactic divisions to check whether it is factorizable or not. Okay, one way to factorize this is you can check whether you can factorize maybe x or maybe x squared. Okay. Let me check the x squared. So if you have this x cubed, so let me factorize x squared. Okay, so only this part. Okay, and I can also write this. Is it the same thing? Same, right? What's next? Let's factorize this x plus 2. Okay. Okay, right? Correct? And then I can write this also in expansion of the factors. And you get your each factors. Okay. But if you don't get this factorized, you can use the polynomial long division or syntactic division to find this. For example, okay. So all we need to assume, okay, some of the parts on this uh, equation need to be factorizable. If not, then we cannot solve and we cannot find the partial fraction. So let's just think any number that makes 0. Okay. So what number that makes 0? So for example, your qx okay. You can try 1 or -1, the easiest number that you can just compute this. Okay. So maybe 1. 1 plus 2 is 3. 3 minus 2, 3 minus 1 is 2. Minus 2, 0, right? So 1 will be the factor. Okay. So because 1 is factor, so let me write the q1 is 0. So 1 is the factor. So I can divide this with 1. So 1, 1 become 3. 3 plus become 2. 2 is 0. Okay. So we get 0 here. So I can write this x minus 1 is what? X squared plus 3x plus 2. In which we can also factorize this, become 2 and 1, right? Because it's 3, right? X plus 2, x plus 1. Okay, same results. Okay, so you can see if you can manipulate the algebra, factorize the x squared, and you can see that it has the same x plus 2. You can factorize them. But if you cannot think like the left one, you can just use this. Okay, see whether you can find any number that can be 0. Okay, so that will be your factor, and you can get the same results. Okay? And then from this qx, we can write down that. Let me just copy this first. So the first one, we have three distinct and then we can write A, B, and C. And what is happening next? We need to find the A, B, C. Okay, we need to find A, B, C. So we need to imagine it's combining together, and we need to find what multiply A that will be resulting the same as the left equation. Okay. So A will be multiplied with the other x plus 1, x minus 1, plus B, x plus 2, x minus 1, and then plus C, x plus 2, x plus 1. Okay. And we solve all the form here. So it will be A let me write the result here. So this will be a x squared minus a plus bx squared plus px minus 2b plus cx squared plus 3cx plus 2c. And this should be equal with the 5x plus 7. And then we can group all the x squared, a plus b plus c, and plus x is b plus 3c, and then the constant will be minus a minus 2b plus 2c, should be equal to 5x plus 7. A plus b plus c is 0, okay? B plus 3c is 5. And negative a, negative 2b, and then plus 2c is 7. Can you check, is there any mistake that I make? No? Correct, right? Okay. And then we can solve it. Let me write the plus b plus c 0 plus minus b plus 3c is 7. So b plus 3c is 5. We can add this to 6c plus 12. So c is 2. And then we can also minus the part become, so b is negative 1. Then a plus or negative 1 plus 2 is 0. So a is what? 1, right? So we get c equal to b equal negative 1, a equal 1. So we can write as a is 1, so 1, b is negative 1, -1 over x plus 1, and then c is 2. Okay. Any questions here? Okay. If not, then I believe you can solve this, okay, on your own. Okay. And maybe to make sure that you can do the calculation effectively, you can count like how fast you can solve this. Okay. And because there will be a lot of expansions maybe in the partial fraction problem like this one, you need to be careful, okay, when you're adding and subtracting. So if you already got this 1, -1, and +2, if you still have time to make sure that it's correct, then you can reverse and then check whether whether it is going back to the original question or not. Okay. If different, then this is not your answer. Okay, this is not the answer. Okay. 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 Now the second one, repeated linear factors. So it will be like okay. So it also can be the same linear equations inside, but it can be like factored, like squared, cube, and so on and so forth. Okay, let me give you the logic, okay? Because sometimes you are wondering why, if we have this cube, why we can factorize become 1 squared and then cube. So if you think this as element A and element B, okay, you can separate those elements and you can write like x, okay, and then plus. Let me write as it is, okay, x and x minus 1 cube, okay. So first, because it is linear, okay, it's on the x, then this will be a constant, okay. And this is a cube, right? So the top one should be 1 degree less, right? Yes, ax squared. Let me write bx squared plus cx plus d, okay. Notice that you have 1, 2, 3, 4 constant, a, b, c, d, okay. Now, if you think this cube, okay, if you want to separate this and separate the c and separate the d, okay, become all by own on their own, okay. So bx squared over x minus 1 cube, and then cx over x minus 1 square cube, and d over x minus 1 cube. We can simplify them, and then we can write as let me chart this first. So we can write them as ax plus b plus C, and then plus D. You can check later, if you combine these two, it will bring back the bx squared and plus cx. You can check the B and C. So if you want to check like the x1 minus 1, x minus 1 squared, so this will be b x minus 1 squared plus c x minus 1. And this will bring back to here, right? Okay. So you get the idea why this will be repeated linear factors. Okay. So it's actually you can prove that by yourself. Okay. That this is the a, B, C, D, and then if you have repeated linear factors like x cubed or x minus 1 cubed, then you can separate the cube, become x minus 1 squared, and x minus 1 cubed. Okay. And the rest, like to find A, B, C, D, is the same. Okay, the same thing that as we did before. You need to look for A, B, C, D, and then grouping the x cubed if there's x cubed, x squared, x, and then the constant, and then solve A, B, C, D. And then the other part is the third case is the irreducible factor. Okay, let me write the qx is ax squared plus bx plus c. If your discriminant or the b squared minus 4ac is less than 0, then q will be irreducible. So that means we can write the q as it is. Okay. So the top equation will be the linear equations like that. And then that's the third case. The fourth case is when you have the irreducible factors, but it can be repeated. Okay. So repeated so you will have, based on the irreducible factors property, you can have, and then you can have the second one, and plus until some constant k. So when you have, for example, when you have this, you have x cubed at the bottom equations, x cubed, x squared plus x plus 1, x squared plus 2, and then the cube. Check the discriminant, -1 minus 4. So it's negative, right? So you cannot reduce this. So this will be as it is, irreducible factors. So how many constant will we have? Okay. So this will be three constants here: x, x squared, and x cubed. So a, b, c. Okay, and here d, e, and here 6, 6, right? 6, 3, 2. So 5, 6, 11 constants. But I won't give this in exam. Don't worry. This is too much. So you are writing the a over x plus b over x squared plus c over x cubed, and then plus the x plus e over the x squared plus x plus 1, and then plus fx plus g, and then plus the hx plus I, and then plus jx plus k, and then that's it, the constants. This is just um, to help you understand how many constants that we can write from these equations. Okay. Not necessarily to solve this, but at least you understand how to separate the each fraction, okay, each fraction. Okay, any questions? So the quiz will be Wednesday, right? Next Wednesday or Tuesday? Do you want Tuesday? Wednesday? Wednesday. So next week on Tuesday, because we don't really have much time, I need to go to another section chapters for next week for Tuesday. Tuesday I will go to chapter 12, the sequence and series, but maybe just an introduction, like really light, not really heavy. And most of the chapters is, I believe, repetitions from your high school. The sequence and series, you get it right in high school, right? Or who didn't learn, who haven't learned sequence and series? Like you know the arithmetic, geometric, right? You get it right because that's among the basic. You learn, right? Still remember? No. Okay. Geometric? No. Okay. Remember? Okay. Okay. I think I will finish this up until here.